Hi, welcome to the end-to-end machine learning part 1 video. In this session, we're going over the process of framing the problem. So the first thing that we will do is to understand how to analyze the problem, how to ask the right questions to be able to look at the big picture. We're going to talk about data collection and then how to prepare the data for machine learning algorithms. So we're going to learn how to handle missing values, how to transform our data, how to create some features that will improve the quality of your models. Okay, so the first big thing before you start, working on training a model is that you need to understand the problem. So why machine learning projects fail? So a common solution is because of the framing, the original problem was not clearly understood, or maybe the solution was not aligned with the problem. So let me just show you a quick example here. In this problem, the idea was to count the number of boxes on a shelf. So imagine that you just finish your master in data science or in machine learning, AI. So of course you want to use your tools, right? So in this case, the expert tried to use like a computer vision or image recognition to identify the boxes. That was the idea, and to be able to count them. But it's not simple, especially if you have like different shapes, and like if the shelf is big, there can be some mistakes. For example, here, adding two boxes in the same square, so you're not counting them correctly. There are other solutions in this specific case. So there is, like existing technology, such as, barcodes, RFID, that will help you to count them and keep track of the boxes, and that technology, was designed especially for that. So you gotta be careful. It's not like you can use machine learning or AI in every single problem. So it is important to frame the problem correctly, to analyze different options before you start applying, like these tools. Okay, so during the problem framing stage, we start with a discovery phase. So this is where we understand the problem, because you need to keep in mind that you can't solve what you don't understand. So if you are new to a company or if you're working as a consultant, you need to, like ask the question to all people that is involved in the process. You need to understand what is their perspective. You need to understand what they're trying to do. You need to understand what they do right now, so you can, like move forward in developing some models. So it's important to have, curiosity at this stage, so you can understand the process and be able to identify the right solution. Just to give you some ideas, this is just like some proposed questions that will guide you in this stage. So you need to ask, what problem are you trying to solve? So you need to clarify this. What problems do you want to ignore? So this is very important, because when you start, like talking with the people that is involved in the process, they will tell you, different problems. Some of them are related, some of them are disconnected. In most of the cases, you cannot solve all of the problems that they have. So you need to focus. You need to be, clearly identify which is the relevant problem, or at least the problem that you can, like solve with the skills. So it is important, again, that you don't try to solve everything right away. You need to frame the problem correctly. And in some cases, that implies that you will need to prioritize some problems before you can solve the other problems. You need to understand who's the customer, who's going to use your solution. So there are some, like internal customers in the company, some external companies. So it's important to talk to them to understand the existing solutions. So this is what we call the as is. How's the as is? So currently, how do you solve that problem? What is the current state of the process, right? So this is really important, because you need to understand what they do right now, so you can propose a better solution. In this stage, it's important to identify like a baseline metric or metrics. So it depends, whether it can be a cost, or time or a prediction accuracy. That will depend, of course, of the context, the problem that you're dealing with. Okay, so once we want to create a model, it's important to make assumptions. Remember that regardless you are using a mathematical model or a machine learning model, there are always assumptions, right? So you need to identify, okay, which assumptions are like possible in the context, right? Then you need to understand, okay, what could make this fail, some potential problems. You need to analyze if there are some, like outliers or diversity, let's say, in your data that can affect the performance of your models. So it's important to understand this, what could make this fail. Then you need to start thinking about, okay, how's gonna look like a simple version of this, like a prototype. And how can we measure the success of the project? So this is very related with the baseline. So you need to, like have a clear picture of all of these questions before you start developing a solution. So let me give you a couple of examples of framing the problem. In this specific case, this is for an application for Disney. They were trying to identify, like people that were breaking in the park without paying the ticket. So the as is process, the way it works is they had some cameras, of course, and then there was a team, and they were reviewing the videos. So there was no initially there was no like a model identifying things. That there were just a team of reviewers. The challenge is like, of course, imagine the volume of Disney, right? It's like you have a lot of people entering the parks. Also, you have a lot of cameras, not just one camera, a lot of cameras. And so the task was overwhelming for the human reviewers. So they requested some help from experts in machine learning and AI. And the idea was to classify or to identify, like when someone was trespassing, right? Or someone was entering the park without paying a ticket. That was the main idea. Now, when the team was trying to identify that, to classify that, they found that it was not easy because there are multiple ways in which someone can enter the park without paying. So it was difficult to find like an accurate model that will do it, like by like with a perfect accuracy or with a good accuracy. It was difficult. But what they discovered is that it was more simple to identify if like which part of the videos are important for reviewing and which parts are not relevant for reviewing. It's like, okay, we cannot perfectly identify when someone is entering the park without paying, but we can find like some specific moments in which there is a high risk that something's gonna happen. So that's why they developed an anomaly detection model. So what the model does is like it filters the data. So instead of analyzing, hours and hours of video, it will discard the portions of video where everything is fine, where there are no anomalies, where most likely most of the people are, paying and entering the park. But if there are some small, sections of the video where there are some anomalies, it means, like a lot of people trying to enter the park. So there is a high risk that someone is gonna enter the park without paying. Then they will send that to the human reviewers, which they were already at the company. So, but now they were receiving, like less hours of video. So they were able to filter like more than 90% of the hours of video. So now the workload decreased, and it was possible for the reviewers to actually identify more clearly when people were, like entering the park without paying. So again, the experts of this case, they said, hey, if we try to classify the, like if someone is entering the park without paying, that project will last, I don't know, more than a year. But with this solution, in few months, they were able to develop something that was feasible for the company and for the team. So the way you frame the problem is critical, because you don't win just by developing good algorithms or having good data. You also win by framing the problems in a way in which success is inevitable. All right. So as important as framing the problem, framing the project, you need to develop some prototypes at the beginning and during the discovery phase. That it's I think it's easier right now. Like with the all AI technology that we have available, with the LLMs, it is possible to develop these prototypes very fast and see how they work before we actually like develop the complete solution. So not every single problem requires machine learning. Remember that you can start just by using some heuristics or rules, some business rules that will help you to create, like maybe like a baseline. Just let me give you some examples. If you're trying to create a chatbot, a heuristic will be, like the old chatbots with some decision trees where there are some predefined questions. Again, it's not ideal, but at least it's a baseline for your comparison. Similar, in another example, imagine that we're trying to develop like a recommender system. So a rule here will be, okay, if a user watch, let's say, the first movie in a trilogy, then the recommendation will be the second movie, which makes sense, right? That's a basic rule. So you can, again, create some heuristics or business rules to test or to compare with the solution that you're going to propose. Okay, this is really important. While when you're learning machine learning, I know that most of us we want to develop, we want to build some, we want to train some good models, nice models that will perform, with high accuracy. We want to use state-of-the-art models, right? And we want to, do the hyperparameter tuning and, like all the things that you are going to learn throughout these courses, which is fine. But you need to keep in mind that good models are fine, but good data is better. I mean, if you have good quality data, even a simple model will do the job. So keep that in mind. Now, what is the ideal solution? We need to combine both. We need to have good models, but also really good data. Now, what is good data? Well, it has three main characteristics. So first, high quality. So what is the meaning of high quality? So first, that it contains predictive features. It means that we have some variables that are really connected with our outputs, with our dependent variables. So that's the meaning of good predictive features. So that these are really correlated with the targets. Our labels are fine. This is a challenge because during class you get, and even if you're using a textbook, most of the data sets, they are perfect data sets. It's like you have complete information, there are no errors in the labels, but in real life, that's not how it works. In some cases, you will find, not some cases, in most cases, initially you will find, like a lot of problems. Wrong labels, missing data, that's another problem, right? Missing values. And you need to do something with that because some algorithms won't work if you have, some missing data. So you want data that is free from errors and the format is clear. So that's the meaning of high quality, right? Then the second characteristic is you want to have a diverse data set. It means that our data set looks like real life. It means that it's capturing what happens in the business on a daily basis. This is really important because you're going to train the model with that. The assumption is that the training data set it's similar to the real data. So in diversity, we need to include even some outliers, like some events that are weird. This is important because you need to see how your model is going to perform under these circumstances. You need to understand those outliers and see like if they are possible or if they are errors. So it's important to keep an eye on those events. You need to represent, like all possibilities or the subgroups proportionally. So the sampling here is important. It's really important. So it's not just random samples. You need also what is called a stratified sampling, especially if there are some really important variables in your data set, or if your data set in the real life is heterogeneous. So the sampling is really important. Quantity, of course, the volume of data. You need to have enough data to be able to generalize, the predictions. Now, volume is not everything, but of course it's important. There are some guidelines. They are not, let's say, strict guidelines, but at least they give you an idea. If you have a simple model, let's say a linear model, people will recommend you to have at least 10 observations per variable. So just to give you an idea, you have, let's say, 5 variables, then you need at least 50 observations. That's for a simple model. Again, that's not like a very strict rule, but at least it will give you an idea. What I think is the important thing about the rule is like it gives you an idea that the number of parameters of your model, kind of like it's important when you are collecting the data. It means that if you're using a complex model, and that model has a lot of parameters, like a neural network, then you will need more data, right? That's the key idea right there. Okay, then there is a phase that we call the feature engineering. Again, you will be given most of the courses and in real life a data set or multiple tables with data, and you don't have to use that data like in the current state. You can combine some variables, you can even combine some observations, create some metrics using that data. So that's what we call feature engineering. So this is the process of transforming the raw data into inputs that will help you to improve the accuracy of your models. So there are, of course, multiple ways to create these features, and there are no fixed rules for this because it requires a lot of business context. You need to know really the context of the problem so you can create better features. So let me give you some ideas on how can you do that. So there are some domain-specific features. So, for example, in finance, you can add some moving averages. It's like, okay, I want to find the average of this variable, using the last 5 months, the last 6 weeks. So that will help you as a metric to predict future values of the output. So that's a possibility here. But again, you need to know the context before you do this. Same thing with volatility. You can measure the variance maybe of the stock prices and use that variance, that metric, like to predict. You can use also a time window for that. In e-commerce, you can create new variables or new features. For example, if if this buyer it's buying from you, like different times, it has a history with you. You can add a variable, like to reflect that. Or also you can use days since the last purchase. You can compute that variable, and maybe that will help you to make a better prediction about the next purchase. We can create new features by combining 2 or more variables in our dataset. So let's say that we are using a machine learning model in healthcare, and we have in our dataset weight and the height of the person. So maybe you can compute the BMI, which will give you more information. So instead of using these 2 as independent variables, you can use this metric, the BMI, the body mass index. Total price. This is another example. You have a variable, one column with quantity, one column with unit price. So it's possible to compute the total price, and that's going to be your future. Now, it is important to mention that by creating these features, there is no guarantee that the model is going to improve. You need to test that, right? You need to check if it makes a difference or not. You can know that beforehand. It's mandatory for you to try this analysis. In some cases, they make sense, like they make a lot of sense. But again, you don't know for sure if they're gonna boost your accuracy. in the models. Okay, let's see more examples of feature engineering and some strategies. When you have times, dates, you can break them down. For example, imagine that in your dataset you have a column with this information: 2025, August 27, and then you have the time, the hour. So it is possible to extract some specific feature: the year, month, the hour, the quarter, if you want, date of the week, if it's day or night. So depending on the context of your problem, it will add value to your model. Here we have more examples. This is like the dataset, a very simple one, only two columns, price and a date. So here there are three different strategies to do some feature engineering. The first one is the binning. Binning means that we're transforming a numerical variable into a categorical variable. So here is, for example, the price is under 50. So if it's under 50, for example, the first observation is 33.99, it's below, right? It's under 50, then it's equal to 1. But if it's above or equal, then it's equal, the variable is going to be 0. So this one, the second observation is 63.5. Then the new feature is equal to 0. So you can, do this transformation from numerical to categorical. It's very common, especially I have seen that a lot with the age, for example. Let's say instead of having, like the age of the individual, you can create some categories that, like below 18, between 19 and 25, you can create those categories. Again, you don't know for sure it's gonna improve the performance. You need to test them. Now, with the date here, we're creating two features: the quarter, and whether it's a holiday or not, that specific day, for example, Veterans Day or something like that. This is another featuring strategy here, clustering. So what they're doing is they are clustering the data. So they're grouping observations that look similar. For example, in this case, these two, they look similar, right? 63.5 and 60. Yeah, they are close to each other. So most likely they belong to the same cluster. And same thing with the last two transactions, right? Or observations, 11.10 and 10. They look, that's why they belong to the same cluster. If you do like a k-means analysis or something like that, you see that observation, the second and third observation, they belong to cluster 1. And the last two observations, they belong to cluster 3. And of course, the other one is not related to, so it's a different cluster. Again, this is just an option. So group the information, create cluster, and this is a new feature, maybe to find a relationship between the observations and the output or target variable. These are just some examples on how to, create the features, the feature engineering. With the key idea here is to use the context, to use existing variables to create more meaningful features for our models. Once we have handled, the creation of these features, typically you're going to scale those features. This is important because remember that your variables, they might have different units, maybe in some case one column is about money, another column is about age, another column is about weights. So different units, different values. So for some algorithms, it's useful if you standardize or normalize the data. So the next thing about doing that is like then your variables are going to be, with similar mean values, and that's going to make the models more stable in some cases. There are some algorithms that they don't care, to be honest, but in general, this is a good practice. So let me show you the difference between data standardization and when you normalize your data. So when you standardize your data, this is related with the normal distribution. So you take for each column, this is your variable, this one, x, the input in this case. So xi is each observation, each value of the variable. So here we are removing from each observation, we do that observation minus the mean value of the whole column divided by the standard deviation. So when you standardize, the nice thing about this is that the new variable, the mean value, is equal to 0, and the standard deviation is equal to 1. So once you standardize, when you remove the mean value and you divide over the standard deviation, again, the new variable, the standardized variable, the mean is always equal to 0 and the standard deviation is equal to 1. So now it has a meaning because, for example, if it's minus 1.46, it means that that observation is below the mean value 1.46 standard deviations. Now, if it's positive, let's say 0.87, that means that this value, the 4, it's above the mean value 0.87 standard deviations. That's the interpretation when you standardize. If it's equal to 0, it means that the value is equal to the mean value. That's the interpretation. Okay, so one nice thing about the standardization is like typically if your data is symmetric, most of your observations will be between -3 and 3. So you can identify outliers, just by looking at the values. You can see some observations that are, like far away the mean. If they are greater than 3 or less than -3, it means that those are outliers. Okay, when you normalize the data, it's each observation minus the mean value divided by the distance between the maximum and the minimum value. So this will give you a value between 0 and 1. The problem with the normalization is if there are outliers, they will affect your number. You will get small numbers. If you have a very high, value. Now you can play with the normalization. Typically it's between 0 and 1, but it's possible to change some parameters and it will be between -1 and 1. It depends what you need. But again, these are the two most popular ways to scale your data, to standardize and to normalize. How to handle missing values? There are different strategies and there is no just one right answer for this. So what are the possibilities? Let's say here, for example, here we're missing one observation. So you need to check your data set for this variable, sex, for example, for gender. So, okay, what percentage of, like that column is missing? So if you see like it's a high percentage, like 60% of the observations do not have that specific variable, then one possibility is to remove that complete column. That's one option, to remove the column. Again, that will happen when you have a lot of missing values for that specific column or for that specific variable. If you feel that is not that relevant in your context, and it also depends on the number of observations that you have. If you have like a very limited data set, then you need to like consider all the possibilities. Okay, what is another option? Let's say I'm missing this value, but I notice that it's not common. It's not that in general this column I have most of the values, like I don't know, 95% or more. It's very complete. Then in that specific case, instead of removing the column, I can remove only that observation. That's another possibility, just to remove the row in my table with that missing piece of information. That's a second alternative. Now there is another option, which is to make some imputations, to impute the values. So in this case is to guess the missing value. Of course, you can make an educated guess. There are some strategies for this. It's not just you're gonna guess it just by looking at the table. No, there are some strategies to do that. For example, you can, if it's a numerical variable, you can use the mean value. In this specific case, if it's a categorical variable, which in this example, you can use the mode here, the most common value, right? Or there are some other algorithms that will help you to perform the data imputation. In some cases, they will look, like the similar observations, and we'll try, okay, for the similar observations, what was the sex value, the gender value? So using that type of algorithm, you can impute the missing information. Again, here, there is no like you should always use this strategy that no one's going to advise you that. It depends on the problem, right? You need to analyze the missing data before you make a decision. But these are some of the three options that you have. Again, remove the complete variable, remove only the observation, or try to make some imputations. And for the imputation, there are more options, of course. There are different algorithms and strategies. This is really important. We need to vectorize our data because computers and models, they only recognize numbers. A computer will, at the end, they're going to process numbers. It doesn't matter if your data is text or images or video. Everything at some point needs to be vectorized. You need to vectorize your data into numbers. So let me show you an example. The first one here, we have this is our original data set. And here we have two categorical variables, the color, blue, green, red, right? And the size. So we can perform some label encoding. This is one strategy. So the idea is like you assign a value, for example, for the size, you can assign a value for each observation, like L means one specific value, or M, medium, another value. So it's like one is 0, the other one is 1, 2, or 3. So for this variable, it makes sense to have, like you have small, medium, large, extra large. If you do some label encoding, like, okay, this one is 0, 1, 2, 3, 4, it makes sense because there is some sort of, like there is an order, right? It's like this one is bigger than this one. So it makes sense. But in the case of the color, blue, green, red, green, like here in this one, you can assign the numbers, right? But there is no order, right? So in this specific case for the color variable, I wouldn't advise this type of encoding. For the size, it makes sense, but for the color, not really. Now there are more options or more alternatives for that. For the color, right? You can use what we call the one-hot encoding, which is very popular. So what it does is that it creates more variables. So in this specific case, the color variable, it has 3 levels: red, blue, and green. Three possible values. So that's why here you are having 3 columns, right? Because now the color red means is it red? So if it's red, then it's equal to 1, and the other variables are equal to 0. Right? If it's blue, then color blue is going to be equal to 1, like the second observation. Or if it's green, the third column is going to be equal to 1, and the others are equal to 0. So this is one-hot encoding. It will create we call this like indicator variables that are 0 or 1. In some cases, there are algorithms that require to remove one of the variables. For example, linear regression, if your variable has 3 levels like here, you will need to create only two variables, just red and blue, for example. But that's just for specific algorithms. In other cases, like trees or random forest, they don't care. They don't. I mean, yeah, it's not relevant to drop one of the levels. Just keep that in mind, because when we are training our models later in other videos, maybe we will discuss, the part of whether we need to drop or not the one of the new variables when you are doing the one-hot encoding. If you have text, you need to tokenize your data. So this is the original text, the sentence. Then we standardize, we remove, like the some signs or punctuations. Then we tokenize. So we break down the sentence into words, right? Or even smaller units in subwords, it depends. And then we index the words. Again, we're translating, text to some numbers. So our computer will be able to understand that. Otherwise, you cannot do it with just text or the image. At some point, you need to translate that into numbers. So that's what we call to vectorize. In this case, it's tokenization because we're talking about text. So at the end, this is not for the end-to-end machine learning, but it's at least for the training part. We need to create a training pipeline. So where we have our data, the idea is that this data, like we're getting data in real time, basically. Then we know how to transform our data, the feature engineering. We know how to handle the missing information. We know how to clean our data in general to create the new features if they are required. So here we have features and labels. So once we have automatized this problem, of course, we train our models. We evaluate the model or models, depends on the situation. And of course, we register the performance, new model, old model. In some cases, we will need to update the model but we need to, register and keep track of the versions. So just to conclude what we have learned here, remember, every time you begin a machine learning project, you need to look at the big picture. You need to understand the problem clearly to evaluate whether machine learning is required or not. What are the options that we have? And even if it's required, you need to be smart in the way in which you frame the problem, because you need to ensure that the success it's going to be a fact in the way you are framing the problem. Good data, it's better than good models. That's true. You need to remember the three characteristics: quality, diversity, and quantity. That's important. And it's better if you combine both, right? Right. Good data and good models, that's the perfect match. So do not focus just on the good models. Remember, you can improve even your data. It's like, don't think that, okay, this is what I have and this that I will have forever. No, you can keep adding more features to your data. You need to keep working always in the quality of your data. That's really important. You need to prepare your data, like clean your data. You need to define some strategies and how you're going to handle missing values for that specific problem. The encoding part, how you're going to handle the categorical variables, the vectorization is also important, of course, and create a pipeline that can guarantee the reproducibility of all your operations. Okay, I'm going to stop the video for now. I'll see you in our next lecture.